So we're going to be looking at some applications to mechanics for vectors. I suppose an important thing to remember is that vectors, we are covering them within the pure section of maths, and that's because they just have so many wide-ranging applications to so many different areas. So not just mechanics, they sort of apply in physics, engineering, computer science, even statistics for data analysis, data storage. They're used all over the place. They're, in the same way as you could just say regular numbers are just inherent to everything. So vectors are not specifically something that are unique to mechanics, but we are going to see a few applications to mechanics in this case. This section in the book is actually quite short, in that there's not really too much content-wise, mainly just questions to practice using what you already know. So I won't be talking too much in terms of explanations. It'll mainly just be a few questions for you to try, and you can see how you get on with those. So yeah, let's just see a few things that I do want to cover though. Let's take a look at that. The main things worth noting that we're going to use them to represent are classic three: displacement, velocity, and acceleration. Now remember, all three of these are vectors and they still make sense when they're 3D, right? Because all that's changed is you're now talking about motion or movement or speed, I should say velocity, acceleration, and so on, happening in a three-dimensional space. So if anything, 3D vectors are almost more real because it applies very specifically to this 3D world we live in, at least in terms of space being 3D. Displacement's a funny one that sometimes gets missed out. It is a vector, right? Because if I say, I started here and now I'm over there, I've in some sense given you a distance. Well, I haven't explicitly given it to you, but you could work it out. But there's also a direction, because to get from point A to point B, from here to there, you have to, if you go in a straight line, walk in a specific direction, and likewise in 3D space, So displacement's a vector, velocity is a vector, acceleration is a vector, same as before, except the direction is, in some sense, three-dimensional. Magnitude, of course, is still a one-dimensional quantity. The size of a vector is always 1D. It's just a single number, a single positive number. In addition to that, just worth mentioning, I suppose, not worth mentioning, very importantly, force, okay, which is what I think we're mainly going to be looking at in this section, is the fact that we still use force, we still use vectors to represent forces, and when we think about a force, we should think very much about the fact that it has a direction. One thing that we're not going to use right now, but you will probably use in other parts of mathematics, is to remember that translations can be described in terms of vectors, right? So when you have an xy coordinate axis and you have a graph on it, and you say, it translates, I've translated this graph, it's moved 5 left, or it's moved 3 up, or it's moved 3 right and 2 up, or something like this. You would sometimes describe that as a vector. You'd say it's been translated by 3, 2. In 3 dimensions, you can talk about translations as a 3D vector. And although, unfortunately, it's not included in the standard sort of core content, 3-dimensional graphs can be translated, and those translations are described in terms of 3 dimensions. Cool. Okay, so to just remind ourselves what we're using these vectors for in the first place. Okay, so within engineering, within mechanics, these tend to be what we use them for. And I'll just get rid of translations because we won't be looking at that now. And then to remind you, right, about this extremely important formula, as you hopefully remember. Okay. Let me use a little bit of different colouring here for the important parts. Okay, and remember, the ones that are written in red, those are vectors, right? This is really a vector equation. Okay, and that green one's a scalar. I say that green one, m is the mass, right? So to remind ourselves, this is resultant force. Okay, it's not just force, It's the resultant force on an object as a vector is equal to the mass of that object times the acceleration, where the acceleration is also described as a vector. Okay. Same as before, same as 2D, and it still works for 3D, but it only works for 3D if you're remembering to correctly identify the F and the A indeed as a vector. Okay, so to just remind you of that, and that F represents resultant force, meaning the sum of all the forces acting on a particular object. Okay, so let's look at an example problem. We've not got too many example problems. You're mostly going to be doing a few questions yourself, but let's look at this one together. So I've got a mass 0.5, and you've got three forces acting on it. I guess I'll just quickly write these in an easier to read form. So that is 2 minus 1, 2. Minus 1, 3, minus 3. And 4 minus 3 minus 2. Okay. Find the resultant force R acting on the particle. So easy stuff. This is the resultant force R is equal to F1 plus F2 plus F3. We're just working in 3 dimensions now. So I'm going to add up all those numbers. 2 minus 1 plus 4 minus 1 plus 3 minus 3. See if you can beat me. 2 minus 3 minus 2. And that's equal to 5 minus 1 minus 3. To then just be safe, let's keep it in terms of the same notation as it was given, as the forces were given in the question. So we're going to go with 5i minus j minus 3k. Right. Find the acceleration of the particle, giving your answer in the form, in other words, giving it in ijk notation. Right, so find the acceleration. F equals ma. Remember, these are vectors. The a is a vector there. So in other words, to get the acceleration, we're going to take that force vector and divide by m. So we can quite easily then get that the acceleration is going to be equal to this thing with all the coefficients divided by the m, which is 0.5, dividing by 0.5, same as multiplying by 2. So I'm going to get 10i minus 2j minus 6k. Just to remind you again, in case you've forgotten, this thing where I put a line underneath the ijk, that's just me lazily designating it as a vector. I say lazily, I'm pretty sure it's an official notation. This arrow on the top is also an official notation for marking vectors. So you've effectively got 2 different ways of doing it. This is the sort of more formal way. This is the slightly lazier way. It's effectively a way to get around the fact that when you're handwriting, you can't really write things in bold. So I just put a line underneath to indicate that this is a bold letter. This is a vector. Right. Find the magnitude of the acceleration. Not too bad, right? See if you can do it quickly. See if you can beat me. The magnitude of A is equal to the square root of 10 squared plus 2 squared plus 6 squared. Technically minus 2 and minus 6, but I'm shortcutting it because I know squaring a minus number is the same thing as squaring the positive version. Root 140. Can we simplify that? I don't think so. Okay, that's it. Square root of 140. That's the magnitude of the acceleration. Okay, let's make a note of that up here actually. Okay. This isn't too difficult so far, right? This is really just the same as 2D stuff. It's quite good that you're sort of learning it now, having just done the 2D versions, because I find some year 13s, if If they enter year 13 having not done 2D vectors for a while, they might forget some of this. But this should come a lot more easily to you because it really is just a slightly more general version of the 2D case. Right, so for D, we're going to find the distance travelled by the particle in the first 6 seconds of its motion. That's just a Suvat equation, isn't it? Because we know the acceleration is a constant number. So we're just going to do a bit of Suvat. Again, see if you can beat me. Let's try and practice. I want S. T is 6. U equals 0. A equals root 140. S equals ut plus half at squared. In this case, u is 0, it's half at squared. T squared is 36 times a half, I'll say 18 root 140. I think we can simplify this actually. That's 18 times, root 35 times root 4. Yeah, so that's 2 times root 35. So we get 36 times the square root of 35. That's it. That's the answer. That's the distance it travels. Okay, so not too bad. Very short section of the textbook at least. Just a reminder really of resultant forces and just having a go at using them in 3 dimensions. Okay, so like I say, this is not a long section, so see if you can go through these questions. And if you finish them in less time than you need to, then you can move on to the next section, which is potentially going to be a bit longer and have a bit more practice. Let me just see how many questions I've set you actually. It's 4 questions. Okay, so you've got 4 questions, and this one here is the first. Okay, pretty basic. I don't think you need a hint. Give it a go. Pause the video now. Okay, and let's take a look at the answer. 2 root 29. Okay, in this one you've got 2 forces. You've been given the acceleration as a vector. But you only know one of the forces, so you need to try and find the other one. Okay, again, you're making use of F equals ma here. That's the only hint I can really give if you did need one. Make use of F equals ma. Remember that F is the resultant force. Give it a go. Pause the video now. Okay, and the answer? There we go. 5 minus 3 minus 7. Let's look at the next one. Okay. Oh, let me explain briefly in case we're not sure what this means here. Static equilibrium, it's not moving. And in other words, not moving, not only is it not moving, but that also tells us the resultant force is 0. Okay, so this statement here is just saying the resultant force is 0. Okay, you've got 3 forces. One of them has an unknown component A. Oh, and another one has an unknown component B. So you want to find those, considering what I've just told you here. Resultant forces are 0. And then there's a little bit more information given here. One of the forces disappears. What's the new resultant force? What is then the acceleration and the magnitude? And finally, can you find the angle? I'll let you have a go at this first, but I do want to give you a hint for for part E, if you want it. If you don't want it, have a go at the question. You can pause the video now. And if you do want the hint E, for part E, remember this is using the formula for 3D vectors of the angle a vector makes with either the x, y, or z axis. And then you just have to remember the unit vector j, which axis is that directed along? Is that along the x-axis, the y-axis, or the z-axis? and it should be fairly clear that it's the y, because vector I is the x-axis, or goes along the x-axis. Vector j goes along the y-axis. Vector k goes along the z-axis. Okay, and the answer, let's take a look, is there. Okay, and let's take a look at the final question. Right. This at first may look a little bit more complicated than it actually is in reality. All this is really testing you on is your ability to take what you know about vectors and apply it to the real world a little bit. The first sentence is just giving you an inherent meaning to I, j, and k. So instead of thinking of an x, y, z axis, it's assigning I, j, and k as being some meaningful direction in the real world. You've got a mass of a plane, you've got two forces on it, and then a third force as well, air resistance. And you're taking g equals 9.8. Remember, g represents an acceleration, but the 9.8 is only the magnitude. Let me think about that for a second. Right, so this g equals 9.8. This is not the acceleration of the plane. This is the acceleration of the plane downwards if it were the case that no other forces were applied. Right, so because there are other forces, there's thrust and lift and all these other things going on in air resistance, you know, the actual acceleration of the plane is not just 9.8, it's not just falling out of the sky. So you need to take this 9.8 into account to consider any additional force, you know, perhaps the weight of the plane, something like that, and then use a final resultant force to get the actual acceleration. And then that's quite interesting, because this is going to tell you how is this plane actually moving. You're going to work out, is it going up in the air, is it coming down, you know, how fast is this plane going, and so on. Sort of a bit of a real world modelling situation. So give that one a go. Again, part B, you need to use that formula we've previously looked at of the angle of a vector with an axis line. And again, think vector k, which axis line is that moving along? Okay, so give that a go. Pause the video now. And your answer is there.